Unit 1 Chemistry, Chapter 7, Part 2. So we're now going to look at something called intermolecular forces. This is dependent on the shape, and it's dependent on what atoms we've got in there. Okay? Now, there are forces that hold the molecule together. They're your covalent bonds. Okay? Sometimes you will hear them called intramolecular forces. Okay? That's your covalent bond that in water, for instance, holds your hydrogens, two hydrogens to your oxygen. But then if you've got one water molecule and another one next to it, there's also a force of attraction between those two molecules. These forces are much weaker. Okay? And if, for instance, you turn water from a liquid into a gas, you've still got the strong covalent bonds in place, so the hydrogens are still attached to the oxygens, but one water molecule gets separated from the other water molecule. So it's the intermolecular forces that are much weaker and they get broken when we turn it into a gas, for instance. Okay? Now the type of intermolecular force depends on something called their polarity. Okay? A polar molecule is one which has one end positive and one end negative. Sometimes you'll hear it referred to as a dipole or even a permanent dipole. It means the same thing. Okay? It's got to have two things to do that. It's got to be asymmetrical, not be symmetrical, and it's got to have a polar bond. Okay? A polar bond is one where the electrons are unequally shared. That would occur when one of the atoms that's sharing has much greater electronegativity than the other. So oxygen bonding with hydrogen, for instance. Oxygen is one of the most electronegative elements on the periodic table. So when they share a pair, it's not actually a very even sharing. Those electrons spend most of their time going around the oxygen. So they're going to go round and round and round the oxygen. And then every so often they'll throw in one going around the hydrogen and then go back to circling the oxygen. Because the oxygen's got much greater electron pulling power. Okay? Now, if it's not symmetrical, such as in the case of water, that oxygen, where they're spending most of their time going around, that's now got a slight negative charge. Because remember, it's got a greater than half share of an electron, and electrons are negatively charged. That means that the hydrogen hasn't got enough of a share of the electron, and it's got a slight positive charge. Okay? It's not a full charge, but it is a slight charge. So it's not going to be as strong as an ionic bond, for instance. Now, if you've got two molecules that are polar, then those slight charges will attract each other. Okay? So, in the case of water, for instance, the oxygen of one molecule, which is slightly negatively charged, will attract itself to the hydrogen of another molecule which is slightly positive charge. We can call that a dipole-dipole attraction. Okay, so here's our water. This is our slightly negative sign, and this little symbol here means slightly. Okay, and this is our slightly positive end. Here, this is our dipole-dipole attraction. In this case, actually, because it's a particularly strong dipole-dipole attraction, we're going to call it a hydrogen bond, which if you do biology you might have heard of already if you do 3-4. Okay? A hydrogen bond is a particularly strong dipole-dipole, and it only happens when we've got a big difference in electronegativity, which means hydrogen, which has got one of the lowest, is bonded to nitrogen, oxygen or fluorine, which is a 3 with the highest electronegativity on the periodic table. So if we've got hydrogen bonding to oxygen, or hydrogen bonding to nitrogen, or hydrogen bonding to fluorine, and we've got an asymmetrical shape, so a triangular pyramid, or a bent shape, or a linear shape here with two different atoms in it, then we're going to get a dipole-dipole attraction. If it was tetrahedral, something like methane, then that would then be symmetrical. So that's why this is not shown here, because it wouldn't give you a permanent dipole, because you wouldn't have for lack of symmetry. You would have those positively charged hydrogens equally distributed all around the molecule. Okay? We can tell that hydrogen bonds exist and that they're strong by looking at the melting and boiling points of substances that got it. So if we think about hydrogen bonded to group 6 elements, or sorry, group 16 in the modern periodic table, get with the times, we'll see that we have got boiling points which are below 0, okay, which means they're turning into a gas below 0. If we extrapolate this line down, we would expect that water would have a boiling point of around about -80. Of course, we know it doesn't. It's got a boiling point of 100. So that shows us that there's a strong bond, relatively speaking, holding one water molecule to the next, and that needs to be broken when we are melting or boiling it.